Hello everyone. If you are getting ready for your WAEC, JAMB, or NECO exams, you know there's one topic in chemistry that is absolutely everywhere, the periodic table. So today, we're not just going to go over it, we are going to master it. I'm going to show you how to turn this chart into your biggest advantage in that exam hall. No, really. Think about that for a second. What if you had a map that didn't just show you where things are, but could actually predict how they are going to behave? Well, that is exactly what the periodic table is. It's not some boring chart you have to memorize. It's a treasure map. It's your secret weapon for understanding chemistry and for nailing those tough exam questions. So, here's our game plan for today. First up, we're going to decode the table's layout, how it's all put together. Then, we'll use that knowledge to predict chemical trends. After that, the fun part, we'll tackle some real exam questions. And finally, I'll wrap it all up with a quick summary and my absolute top tips for success. Let's dive in. All right, let's get right into it. To really use the periodic table, you first have to understand how it's organized. And that story starts with two absolute giants of science. It all kicked off way back in 1869 with Dmitri Mendeleev. Now, he started arranging elements by their atomic mass. But his real stroke of genius was leaving gaps for elements that hadn't even been discovered yet. But you know, the table wasn't quite perfect. And that's where Henry Moseley comes into the picture. He figured out that the real key wasn't the mass, but the atomic number. That's the number of protons. That one little change fixed everything and gave us the incredibly powerful table we use today. And the way this thing is laid out, it's brilliant. The horizontal rows are called periods. As you go down from one period to the next, you are literally adding a new shell for the electrons. Now, the vertical columns, those are the groups. And here is the magic trick. Everything in the same group has the same number of valence electrons. Those are the outer electrons that do all the work in chemical reactions. And that's why they all behave in such similar ways. We can also break the table down into four main blocks: S, P, D, and F. The easiest way to think about them is like neighborhoods, and each one is defined by the type of electron orbital that's being filled. So you've got the S block on the left, home to super-reactive metals. Then there's the P block over on the right. That's a really diverse area with non-metals and metalloids. And that big chunk in the middle, that's the D block, where you find all the transition metals like iron and copper. Okay, so now we know the layout. This is where the magic really happens. We can now unlock the table's greatest power, predicting trends. These are like the rules of chemistry. If you understand these, you can answer a massive number of exam questions without having to memorize tons of individual facts. First on our list is atomic radius. And it's pretty much what it sounds like. It's just how big an atom is. Simple enough, right? But here's the question. How does that size change as we move around the table? Well, the answer might not be what you expect. Okay, so here's the part that might seem a little backwards at first. As you move from left to right across a period, the atoms actually get smaller. Why? Because you are adding more protons to the nucleus, and that creates a stronger magnetic pull, yanking those electrons in tighter. But as you go down a group, the radius gets bigger because you are adding whole new layers, whole new electron shells. Next up, we have ionization energy. This is all about how much energy it takes to completely remove an electron from an atom. You can think of it as a measure of how tightly an atom holds on to its outermost electron. And what's really cool is that this trend is basically a perfect mirror image of atomic radius. It makes total sense if you think about it. As you go across a period, the atoms get smaller, and that nuclear pull gets stronger, right? So it's way harder to snatch an electron away, meaning the ionization energy goes up. But as you go down a group, that outer electron is further away, it's easier to remove, so the energy required goes down. Now let's talk about electronegativity. This is another big one. It describes an atom's ability to pull electrons towards itself when it's bonded to another atom. It's all about an atom's pulling power in a relationship. And this trend perfectly explains why some elements are so reactive. It follows the same pattern as ionization energy. Electronegativity goes up as you go across a period, and it goes down as you descend a group. And this is exactly why fluorine, sitting up there in the top right corner, is the undisputed heavyweight champion of electronegativity. It's a small atom with a ridiculously strong pull.
All right, theory is one thing, but let's put it into practice. This is the moment of truth. We're going to use these rules we've just learned to solve some real, actual past questions from WAEC, JAMB, and NECO exams. Let's see how this works in the real world. So, here's a classic WAEC question. They give you a bunch of electron configurations and ask you to sort them out. This is all about testing your fundamental understanding of the table's layout. Go ahead, pause for a second, look at them, and see if you can figure it out before I walk you through it. Okay, you ready? Let's break this down. For part 1, finding the group, all we have to do is count the valence electrons, the electrons in the outermost shell. If you look at Q and S, they both have 3 valence electrons. Boom, same group. For the period, we just look for the highest shell number. For Q, T, and U, the highest number is 2. So they're all in period 2. See? It's a system. Once you know the rules, you can solve any part of it. Now here is a typical JAMB question. This one goes a little deeper. It's not just asking what the trend is, it's asking why it happens. So what's the fundamental reason that ionization energy increases as you move across a period? And the answer is B. It's because of the increase in nuclear charge. As we move from left to right, we're packing more and more protons into that nucleus. That stronger positive charge pulls all the negative electrons in tighter, making it much harder to remove one. It all comes back to that simple principle. Let's tackle one more, this time from a NECO paper. We get an electron configuration and we're asked to find the group. Take a look and see if you can figure it out before we solve it together. The trick here is to ignore everything except the outermost shell. First, we find the highest energy level. That's the one with the biggest number, which is n equals 3. Now we just add up the electrons in that shell. We've got 2 in the 3s orbitals and 2 in the 3p orbitals. 2 plus 2 is 4. That means we have 4 valence electrons, which puts our element in group 14. That means the answer is D. Simple as that. Wow, we have covered a lot of ground. So let's bring it all home. We're going to wrap this up with a super powerful summary and some absolutely crucial tips to carry with you into that exam. Okay, this table right here, this is your golden ticket. I seriously recommend you pause and take a screenshot of this. It boils down every single key trend we talked about into one simple chart. This is the perfect thing to look at for a last-minute review before you walk into the exam. And finally, here are my top tips. Just burn these into your brain. Group number comes from valence electrons. Period number comes from the highest energy shell. Remember, it's the atomic number, not the mass, that organizes everything. And please, please, don't make the most common mistake of mixing up the trends. Just close your eyes and picture the table in your mind to keep them straight. And to leave you with one final brain teaser, let's look at iron. Using everything we've covered today about electron configurations, can you figure out how many unpaired electrons there are in an iron 3+ ion? Think it through, apply the rules we've discussed, and see if you can solve it. Good luck with all your studies. You've totally got this.
For more practice questions and solutions, visit examkp.com.